Okay, so let's continue this one. We want to actually take this piecewise function and write it in the unit step function, so it's one function. So we want to have sine of 3t from 0 to pi. Then it needs to be cosine of 2t from pi to 2 pi, and then 0 beyond 2 pi. So we want to first turn on the sine of 3t. So if the rest of this wasn't even here, then the function would just be sine of 3t. But because I don't want sine of 3t beyond pi, I need to subtract off the sine of 3t so it goes away. But I only want to go away at pi, so we're going to multiply that by the unit step function of t minus pi. Remember, unit step function is 1, so sine of 3 times 1 is sine of 3t, and that would make it go away as long as t is beyond pi. Then we want to bring in the cosine of 2t. We're going to bring in cosine of 2t times, again, the unit step function at t minus pi. So that will now turn this one on. It's off below pi. After pi, there's now a 1 there. So now it'll be on. Then we want to turn it back off and make it all 0. So then we'd have cosine of 2t times the unit step function at t minus 2 pi. So that now at 2 pi, it's 1. 1 times cosine of 2t is cosine of 2t. Cosine of 2t minus cosine of 2t is 0. These already were 0. So that's what that function would look like. This theorem just tells you how to do a Laplace transform of a unit step function. When we do a Laplace transform of unit step function, we get this e to the minus as times that function that was the original Laplace transform of the original function, of the other part of what's being multiplied by the unit step function. So we have that theorem. So if we want to go ahead and find the sine of t times u of t minus pi halves, then the Laplace transform of this was we first look at the Laplace transform of sine of t. Again, going to our Laplace transform table, sine of kt is k over s squared plus k squared. So we know we're going to get an k, not s, k, which k in this case is 1. So it's me 1 over s squared plus k squared, but k is 1, so it's 1, times e to the minus s times a being the pi halves. So in this case, it would be pi halves times s. And so that would be your Laplace transform of that. Going the other way is a little bit more work. So first off, we want to find the inverse Laplace of 1 plus e to the negative 2s squared over s plus 2. Well, the first thing is I can't handle that square, so let's go ahead and multiply everything out. So this is the inverse Laplace of 1 plus 2e to the minus 2s plus e to the minus 4s over s plus 2. Then we would like to go ahead and separate this out into separate fractions. So it's the Laplace transform of 1 over s plus 2, the inverse Laplace it is, plus 2 times the inverse Laplace of e to the minus 2s over s plus 2, plus the inverse Laplace of e to the minus 4s over s plus 2. Okay. Now, the inverse Laplace of 1 over s plus 2, again, going to your table of transforms, 1 over s plus 2. Here's 1 over s minus a, so must be 2. My a must be minus 2. So it's e to the negative, e to the at. So this would be e to the negative 2t plus 2 times. Now that e, the inverse Laplace of 1 over s plus 2, we already know is e to the minus 2 times t. But instead of just putting a t there, I'm going to kind of leave that space there. Kind of think of it as I'm going to fill that with something. And then e to the minus 2s gives me the unit step function of t minus 2. Well, the thing is that if you look back at this formula for this, is that it is f of t minus a is times the unit step function of t minus a is f of s. So when we do this inverse, we need to have, if this is t minus 2 here, this needs to be t minus 2 here also. Same thing with this one. This is also going to be e to the minus 2 times something, just like we had before. And I should have given it that much space, so let's just move this back a little bit. So e to the negative 2 times something, and then the unit step function, well, e to the negative 4s gives me the unit step function of t minus a happens to be 4. So again, if this is t minus 4, this is also t minus 4. All right, so now let's actually solve a differential equation with the Laplace transforms of 2y double prime plus 20y prime plus 50y equals 0, y of 0 equals 2, and y prime of 0 equals 0. So this is pretty straightforward. We can easily do this, no big issues. So we're going to have 2 times the Laplace transform of y double prime plus 20 times the Laplace transform of y prime plus 51 times the Laplace transform of y equals the Laplace transform of 0. So the y double prime's inverse Laplace transform is s squared times y of s minus s times y of 0 minus y prime of 0. So remember, the s's are decreasing power, starting with the same power as the derivative, and the y zeros, the initial values are increasing in derivatives. I plus 20 times the Laplace transform of y prime, which is s times y of s minus y0, plus 51 times y of s equals 0. The Laplace transform of 0 is 0. Okay, so now we want to get all the y of s terms together, all the constant terms to the side. Go ahead and put in your what these things are equal to. So y of 0 is 2, y prime of 0 is 0. Now, getting all my y of s terms together, I've got a 2 times s squared plus a 20 times s plus a 51 times y of s. Then I have a minus s times 2, so a minus 4s to the other side. And everything else canceled. Okay, so we have 4s is equal to this. Now we will should have, oh, I missed this plus this one here. Sorry, missed this value here. So that was going to be 20 times negative 2, which is negative 40. So I missed that negative 40, so we're going to have a plus 40 when we bring that over to the other side. Okay. So y of s is going to equal 4s plus 40 over top of 2s squared plus 20s plus 51. Okay, so now we need to do the partial fraction decomposition on this. So we're going to go ahead and do that. So let's see, we're going to have so we're going to decompose that. I'm going to do that fairly quickly here. So we're going to expand 4s plus 40 divided by 2s squared plus 20s plus 51 and we end up with 4s. So y of s is equal to 4s. Well, I didn't need to do this. I could have just separated this out. So because the denominator doesn't factor, so it just separates it out into two separate terms. Since it didn't factor, that tells me the denominator must need to use complete the square to try to separate this into multiplication, because we don't have any that do this. So we would then have 4s over, I'm going to go ahead and divide out the 2 for just a second. In fact, we're going to divide out the 2 and divide it into the numerator. So that'll give me 2s in the top and s squared plus 10s plus 51 halves. So this one would be 20 over s squared plus 10s plus 51 halves. Then we're going to go ahead and divide the coefficient of the s term by 2. So 5 divided by 10 divided by 2 is 5. And then we're going to square that. So we've got s squared plus 10s plus 25 plus our 51 halves. But that means we've changed things. So we're going to subtract 51 halves. That'll be the same for the other one. Oops, minus 50, minus 25, that's right, okay. All right. So we now get 2s over top of s plus 5 squared. 51 halves minus 25, 51 halves minus 50 halves is negative 1/2. Oh, actually positive 1/2, sorry, positive 1/2. Okay. So one thing I noticed is I do have this s plus 5. I know I need to have an s plus 5 in the top. So again, I'm going to go ahead and think about it mean an s plus 5 in the top. What did I really add to the top? I really added a plus 10. So I'm going to subtract a 10. So I'm going to subtract 10 from this term, which since this term has the same denominator as this term, I'm just going to subtract 10 from this one. Okay. So now that tells me I can go ahead and do the inverse Laplace. Y of t would be the inverse Laplace of this, which is s plus 5 over s plus 5 squared plus 1/2. Again, anytime I see an s plus 5 thing going on here, it's going to tell me I'm going to have an e to a power. Again, we can use number 19 perfectly just like this. It's going to be s plus 5, so my a is negative 5. So I'm going to put a negative 5 in here for the a, and my k is the square root of 1/2. So we end up with 2, that 2 was out there, e to the negative 5t cosine of 1 over the square root of 2t. This one's going to be the exact same way. I'm going to pull that 10 out. Same idea, but again, we're going to go look for that that transformation, we see we actually have a k over s minus a squared plus k squared equals e to the at sine of kt. So here, my a again must be a minus 5. My k is the square root of 1/2. That means I do need to add that to the top. So I do need to have, if I have a square root of 1/2 as my k, I need a square root of 1 over square root of, or a square root of 1/2 in the top, which means I need to multiply by the square root of 2 so that it doesn't change things. So I now have square root of 10 times the square root of 2, e, forgot my e to the negative 5t sine of 1 over the square root of 2t. And that's the solution to this differential equation. One more, we're going to do one, but this one is y prime plus y is equal to f of t, y of 0 equals 0. F of t is the piecewise function 1 when we're between 0 and 1, and -1 when t is greater than 1. So the very first thing I need to do is I need to rewrite my f of t with the unit step function. So we know we're going to turn it on at 1. 1 then needs to go off at 1. So we're going to have t minus u of t minus 1 to turn that 1 off. Then we're going to turn on -1 at u of t minus 1. So I'm really adding a -1 here. It doesn't look like it, but I'm really adding a -1 times u of t minus 1. That turns this one on. And now I can see that I actually am going to have 1 minus 2 u of t minus 1. So there's my function. There's my f of t. So now I can think of this as y prime plus y is equal to 1 minus 2u of t minus 1. So now we'll do the Laplace transform of both sides. Okay. So the Laplace transform of y prime, y prime is s times y of s minus y0. Laplace transform of y is just y of s. Laplace transform of 1, again, if I go back to my table, you probably know this one. You've kind of seen it enough times. The Laplace transform of 1 is 1 over s. The Laplace transform of u, well, one thing to remember is that it is not just u by itself. There is a function in front of it, and the function in front of it is 1. So there will be another 1 over s. Remember, the Laplace transform of u is e to the minus a, which in this case is 1 times s. If you can't remember that, on this page, I don't actually have it, but in your textbook, this one actually does show up on the table. So you'll find it on your tables a lot. But you also don't need that. You just need to remember this is going to be 1 over s, and then that e to the minus a times s. Okay. So now, oh, I lost my 2. There we go. So let's put a 2 up there. Okay, so now we're going to go ahead and get the y of s by itself. Put in what y0 is equal to. Up here, y of 0, we were told was 0. So y of 0 is 0, so that is gone. Let's get all the y of s terms together. We've got an s minus 1 times y of s is equal to 1 over s minus 2 e to the minus s over s. Get y of s by itself again. So it's 1 over s times s minus 1 minus 2 e to the minus s over s times s minus 1. Again, you're now going to take out your calculator and you ask your calculator, what is this? And if we were to separate these, do partial fraction decomposition. So when I do partial fraction decomposition on this, I'm going to actually just do it on my calculator because it's always a good idea to do it on your calculator. So we're going to expand this, or Wolfram alpha, or some other way. To expand this, we have 1 divided by s times s minus 1. And that separates out into 1 over s minus 1 minus 1 over s. And then the other one will be, and I actually put in the e in there, even though nothing's going to really happen to that e, it's a good idea to have that in there so you just remember that it's part of it. And so the calculator knows it's part of it. Sorry. It's taking a little bit of time here to type it all in my calculator. And I'm actually, just because I'm a little stickler about this, I like to put even the minus sign in there. So I remember to do all that. Don't forget, you need to have multiplication. You can't just do s times s minus 1. You do need to have that multiplication symbol in there. So we're going to have, this goes as 2, it's positive 2 over s times e to the minus s minus 2 e to the minus s over s minus 1. Now we can do the inverse Laplace of this. So y of t equals the inverse Laplace. So you look it up, and again, going into your table, you're looking for 1 over s minus a. That is actually e to the at. So that becomes e to the at. It is s minus a. So it's, I'm sorry, s plus a. So it's going to be minus t. 1 over s. So we're going to have minus 1 over s is just t. So minus t. Plus 2, 1 over s again is t, but then this e to the minus s is your u to t minus 1. And again, because this is a t minus 1, this has to also be a t minus 1. And then we're going to have this minus 2 here, and this is going to be e to the minus t, and then u of t minus 1. But again, if this is t minus 1, this also must be a t minus 1 in the parentheses. All right, and there you have it.